Hello gamers, Jump Ray here. Wow, I have 2 viewers. This hardly happens. Hello gamers. Oh, I'm streaming on my main channel, that's why. Yo, welcome to the stream. You're all very welcome. I have stream chat open today. This doesn't happen so often, so make the most of it. Call me something in chat, I don't know. Whatever. So today we're doing chemistry, I guess. So that's pretty gamer. Essentially. Where am I going with this? So recently I applied to university and stuff, and on the admission, on the application, you have like a personal statement thing. I was saying how I did like multiple maths, chemistry, and computer science videos on my YouTube channel. And then I realized I've never actually posted a chemistry video to my main channel, Jump Race. I was like, oh no, time to fix that. So I have actually made chemistry videos before, and I put them on my YouTube channel there. So at least there's something. But then I guess I just kind of made this video to like highlight those videos exist. I was doing free radical substitution, but I was kind of like modeling it in Python or something. I don't know. It was a bit wild. Chemistry is a bit wild when you try and apply it to like maths or computer science. So yeah, that's the main purpose of the video really. So I might just end stream that, except I'm not going to end stream because I wanted to make like an actual video. So yeah, so I give myself 30 minutes, and if you have chemistry questions, please ask. That would make my day like a million times better, because it'd be way easier to answer questions than to work from scratch. But I'm probably working from scratch. That's okay. I already asked viewers how they were, weren't they? There's like a small chance, because I put my YouTube channel on my university application. It might have been a great idea. My instructor before I sent off was like, "Are you sure you want to do it?" I was like, "You know, it's going to be great." Extend the application further. Oh dear, to the YouTube channel stuff as well. Alright, let's go into it. So that was just me testing the drawing tablet. Oh yeah, my drawing tablet's just not responding. Like, watch, I'll like write a word like happy, and it's like 10 years later it writes. Oh no. Oh no. I might just use my mouse, it's that slow. Okay, so chemistry as a whole, including AS chemistry at A level, split up into 3 different strands. And those 3 strands are physical chemistry, and then we have organic chemistry and inorganic chemistry. And I guess I kind of wanted to just do the topics. There's 16 different topics that I'm going to go through, various ones from the AS chemistry. I'm a bit sick, by the way. A bit sick. I don't know why. My throat's just like died for no reason. Otherwise, I'm alright. And I'm guessing whoever's watching isn't signed in or something, because there's no chat. At least not yet. Maybe I'll get lucky with that one. We'll see. So 16 areas we're going to cover in total. Where are they from? There's 3 from inorganic. I guess we'll start with the organic ones, what they are. So we look at a whole 3 viewers now. Hello guys. So yo. Oh, I wish we were making math. We're not making math, unfortunately. Welcome to the stream anyway. But you will get better at chemistry, maybe. We could look at where you'd go with that. I'm actually quite interested now. You know, I'll do that in a second, just because. Oh my goodness. And that's what's cool about the stream aspect. People can just like ask questions, chat random things and stuff. So you got the petroleum topic, which is basically just looking at alkanes, but petroleum is sort of the main focus. Then you got alkenes. What do you know about chemistry? I don't know what to call you, because your name is just hardly a name. How can I make that a name? I can call you Big. Yo, Big. What do you know about chemistry? Just out of interest. Do you know anything? Do you study at any sort of level? What else do we look at? Alkene. This is so slow. I'm writing with the mouse. That's slow as well. Let's just type it. Yo. Hey Bill. Just he's being corrected. I'm guessing Jesse's a character from it. I haven't seen it. I should have seen it. It seems good. Seems like the best anime. Oh, you and GCSE, no. Alright, well, we're going to fix that, hopefully. Organic analysis, alcohols, halogenoalkanes. Is that it? It's a good number of topics there, so it might be it. 5 different topics there, so that would suggest 5 plus 3 makes 8 minus 8. No, there's only 7 topics here, so I'm missing a topic here. But I couldn't care less. Alright, so I guess we should start by talking about atoms. I'll quickly look at this, but I'll try and be quick because I know this is just not great top content. We want to get into like doing stuff. So there's atomic structure, AOS, we can talk about that in a second, bonding, energetics is a pretty good topic. Hopefully we'll get onto energetics sooner rather than later because it's pretty sick. It's the 5th topic. I don't know what the 5th topic is. Oh, kinetics. It's a meh topic. And then I'm just going to write there. This is dull, so I'll just move on. Inorganic chemistry is not much fun either, so. Alright, let's talk about atoms. Everyone's favourite. Oh, getting roasted by Bill. Oh, goodness. I wouldn't have that big, personally. Alright, let's start with atoms. So the idea is some like famous philosophy dude was like, I wonder what happens when I split stuff. Actually, let me get a piece of paper for this. This is a demonstration I thought about way too much in the past. No, where's my paper? Yo, here it is. Saved by the pad of paper. Epic. Not sponsored by Tesco, by the way. So the philosopher was like, okay, so I have an object such as a piece of paper, and he noticed that if he took the piece of paper, he could split it in 2 and nothing bad happened. And he realized that he could take the half, split it again to get smaller. And he basically was like, if I keep repeating this process, how small can I go? And he theorized that seeing as it's physical, it's probably not infinite, so he probably can't keep splitting forever. So he essentially was the first either scientist or philosopher to suggest the existence of atoms. And essentially his model of the atom, as he was saying, I don't really know what it is, but he was like, I reckon the smallest you can go in terms of splitting things is a small indestructible sphere. I think it was Dalton who did this. I'm pretty well, yeah, it was Dalton. And he had a few other things he said about the atom, but the essential idea was he pretty much just theorized that something along the idea of an atom had to exist. But his model wasn't so good because it wasn't really based on like data so much as him theorizing its existence. So over time, our knowledge of the atom got better. This is really fundamental. I don't know why I'm going this fundamental to begin with, but it'll be fun. So, so essentially later on we found out the electron existed, and it had to be, I believe, the sort of ways it had to be small in the atom. So we got the next model of the atom, which is the plum pudding model, where essentially the idea is you have a positive thing, and you have lots of embedded electrons within it, and that's what allows the atom to be neutral overall but have electrons. But then later on we found out that's not right either. So we got a model of the atom which has your proton in the middle, electrons orbiting around the edge. But in this model the electrons just kind of like spin around, but later on we realized that if they just span around they get pulled into the center because the center's positive. So the final model, and this one's by Rutherford by the way, so the final model, which is pretty much what we use today. I mean, there's also Schrodinger's model, but it's not too important for like an introduction to chemistry. But the final one we'll look at today is Bohr's model, which is pretty much the one we use. And the idea of Bohr's model is that the electrons are kind of less physical things now and more sort of ideas. Schrodinger even went further and described electrons like as literally just a function, a wave function using Schrodinger's equation. But Bohr was starting to get onto that with his model of the atom. I don't know how much detail he put in. So the question is, how much of this is useful to chemistry? The answer is, it's kind of useful, I guess, to sort of be aware of how the atom, the idea of it, sort of changed. In case you couldn't tell, I didn't fully plan this. I just sort of thought, yeah, let's wing it, it'll be fun. So I'm just kind of going with it. What do people want to learn about? Do people want to learn about physical, inorganic, organic chemistry more? Or do people want like an overview of what each one is? I could do that quickly while I wait for responses in chat, I guess. So physical chemistry is kind of what we went into now, but we essentially extend that idea. And it's basically just all the physics that's useful to chemistry. It's very physics heavy versus anything else, except sometimes the physics becomes more simplified, so it just becomes calculations that are useful for chemists. And the key difference between organic and inorganic chemistry, they both just study different molecules and figure out what different molecules and therefore substances do. But inorganic is non-living stuff, organic is living stuff, and it just so happens another way you can split them apart is organic is compounds that involve carbon, whereas inorganic isn't. You want to do physical, great choice, gotta love physical. Is that like meth and stuff? No, that's organic. I think, let's do a quick bit of research. I don't want to go on too much of a side tangent. Yo, stats leak, yo, that's not okay. Don't want to go too much on a side tangent on this, but yeah, you're already a chemist, bogus. In terms of atoms equals small, you've probably been told about Avogadro's constant before. But if you haven't, that's a really key physical chemistry, seeing as you wrote physical, you didn't know what you're getting into, but that's okay. Avogadro's constant is 6.022 times 10 to the 22. No, it might be 10 to the 23. I should know that number. It's somewhere around there anyway. And the idea is when you have that many atoms, the mass of the atoms becomes its atomic number. So for example, with oxygen, it has a proton number of 8, but a mass number of 16. So if you have that many atoms of oxygen, you have 16 grams of oxygen, which isn't very much like in terms of mass, but it's a lot of atoms. For perspective, that's like a billion squared, because a billion's 9, and a billion squared is 10 to the power of 18, so that's like bigger than a billion squared. So that's a lot of atoms for a very small amount of mass. Okay, yeah, I don't want to side tangent on meth for too long, as fun as meth is. So I'll spend like 3 minutes doing meth research, just because I don't know anything about it. I've never really thought about it. Have a bit. What will that come up with? Nope, that's drug addiction. That's not what we want. Oh, there's its name. C10H15 skeletal formula of meth. Oh, only the best chemistry. Yo, there's its skeletal formula. Do you guys want to learn about skeletal formulas? Because I know I do. I want to talk about it. Alright, we could start with that. This is like a key starting point to organic chemistry, really. To do a set time so I don't spend too long just on meth when it's not really. That's a bit useful, but not that useful. Oh, I won't be wasteful. I'll use the space I've got here. Let's redraw it. Doesn't take too long. So it's a hexagon of atoms here, carbon atoms. The double line means it's a double bond. We can talk about double bonds in a second, because that would be interesting and fun, maybe. I don't know. We'll talk about covalent bonds as well. We'll talk about the other bonds as well. I don't know. There we go. Incredible. And a formula pretty much means we'd usually use its formula rather than its full name. So this would usually be how we'd represent meth. We wouldn't call it meth. We might, but like in notes and stuff, if that made any sense. The skeletal formulas are good because it allows you to save a lot of space instead of drawing every single atom. Essentially, like when you draw like a line like this, every point is considered a carbon atom. So instead of drawing out, I can demonstrate what the full thing would be. So the full thing would be like this. Like you might have seen these. This is called displayed formula. But with the skeletal, we can save a lot of time by just drawing a point and then drawing a line between it every time we want to add more carbons. So it allows you to save a lot of time. You don't write any of the hydrogens in either. Because carbon always forms 4 bonds, it means that here, because it's carbon, it's got a single bond here, but the other 3 are going to be filled with hydrogens. Yo, it's P Yoshi. Yeah, we're learning moles and everything. It's gonna be great. Yo, 5 viewers. This never happens. How come of all things my chemistry stream is doing it? This is what happens when you stream chemistry instead of maths. Just everyone is wanting to watch your stream. I don't know why that is. All right. We'll talk about bonding because it's very important and it's like a key strand, and it'll be productive and it'll be hopefully fairly interesting. So we've spoken about how atoms aren't just single units and that they consist of three different particles within them. We haven't spoke about neutrons, but they're also there. But they're not as important as protons and electrons really anyway, especially as far as chemists are concerned. So the way that atoms bond, so if we take hydrogen as an example, it has an electron. The electron has to go somewhere, so it fits inside what we call a shell. And the more electrons you get, the more shells you have to get. So the first shell can only contain 2 electrons. So if we try to put more, no spam in general. Oh no, the spam is great. That's what you're looking for as a streamer. You want to be bombarded with messages. So you can only fit 2 electrons in this shell. So if you get more than 2, it has to go into a second shell. And if you get more than 10, it has to go into the next shell. And what we call it when we have enough electrons and any more would make it go into the next shell, is we call the shell full. So the atoms, we say they want to get full outer shells, but what we mean by that is they'll tend to move towards a state whereby they'll have full outer shells. So what will happen is if 2 hydrogens get together and they each have an electron, what sort of happens is, because it sort of can happen, the electrons come together and they sort of become a part of both shells at once. And this holds everything together. So it holds the 2 hydrogens together. So hence hydrogen will tend to single bond with another hydrogen and form a H2 molecule. So you won't really get hydrogen atoms on their own. If you've got hydrogen, it'll be hydrogen gas of 2 hydrogen molecules. 2 hydrogen atoms, sorry. Oh no, my man's just spamming balls. Bro. Spam atoms and then it'll at least be slightly scientific, and that can be good. Oh my goodness. So for every 2 electrons in the covalent bond, we call it like a single bond if it's 2 electrons. If it's 4 electrons, it's a double bond. 6, it's a triple bond. So here there's 2 electrons. There'll always be pairs of electrons for covalent bonds. So this bonding is what underlies a lot of chemistry, especially like all of organic chemistry. So if we go back to our meth example, where we got the skeletal turning into the displayed formula and therefore describing how the atoms are connected, carbon makes 4 bonds because carbon has 6 electrons in total, and as we said, the lowest subshell can only contain 2 electrons. So then for any electrons past 2, it'll go in the next shell. So here we've got 6 minus 2 leaves 4 electrons in the outer shell. And what will tend to happen is it will tend to like gain an extra electron 4 times. So each electron will bond with 1 electron from something else, and hence you'll get carbon forming 4 bonds. How do I super chat? You donate money to me. I don't know if you can do that, but if you want to, then that might be an option on YouTube. But I don't know if I'd recommend it, considering I don't know if you're really getting an education here. Maybe. I just need to figure out what kind of chemistry things you might be interested in. I'm not sure. People are turning up anyway. So we discussed covalent bonding. There's also ionic bonding, metallic bonding. There's also van der Waals forces we could look at, which is also bonding, dipole-dipole bonding, and then hydrogen bonding. Yeah, at that moment when you realize you have to pay to do super chat. But we're not going to look at the intermolecular ones, which are hydrogen bonding, dipole-dipole, and van der Waals. We only really need covalent, and then we can do a lot of organic chemistry. I could talk more about organic chemistry. Or I could look at some of the other stuff. There's also physical things. So we kind of looked a bit at this. We could look at weighing atoms. That's pretty cool. So this is something that like kind of blew my mind. I didn't really think about it. It's pretty wild. It's essentially, like I was saying earlier with Avogadro's constant, where if you have 6.022 times 10 to the 23, or what we call 1 mole, it's the same thing. Same way you might have a million, which is 10 to the 6. 1 mole is just a big amount of things. When you have 1 mole of atoms, then its mass number becomes the mass in grams. So I was giving the example of oxygen having atomic number 8, mass number 16. So if you have 1 mole of oxygen, you have 16 grams. But the question is, how do we know that oxygen weighs 16? And the reason why this blew my mind is because someone pointed out you can't just put an atom on a set of scales. Air pressure is stronger than the gravitational pull of that atom to the Earth because its mass is so low. So you can't just weigh it, but we still know its mass. And the way we do it is actually wild. So what you do is, it's called mass spectrometry. There's some different types, but the one I know about is time of flight mass spectrometry. So first of all, you'll either use electron spray ionization or electron impact to charge the atom. So however you do it, it'll end up being oxygen plus. And then you, depending on whether it's electron impact or electron spray ionization, you essentially use something to accelerate it through a tube. And you measure how much energy you're inputting to accelerate it. And then you can use this equation, it's wild. It's E equals a half mv squared. Like this. And you can use this, since we can figure out its velocity basically, because we can time when it gets here. We have a detector plate here that tells us when it goes from the start to the end. And we can time how long it takes to get there. We can measure the distance of the tube. So we can get velocity because we've got distance and time. And velocity is the time taken. No, sorry, the distance traveled divided by the time taken. So we got distance, we got time, so we got velocity, and we know how much energy we inputted. So using this physics equation, we've got all the variables except mass, so we can rearrange for mass and find the mass of the atom. So it's pretty wild. So that's a pretty exciting part of physical chemistry. Interesting to see what Vanderbilt's a funny original joke. All the money needs to go towards his meth addiction. Well, I can't help you with that, but I can talk about a bit of chemistry. So yeah, there you go, chat. That's how we measure the mass of atoms. Exciting stuff. We've spoken about bonding a bit. We can also talk about the shape of stuff. I mean, it's only exciting after you've done enough bonding when you suddenly realize it's 3D and not 2D. You know what? It's cool. It's cool. We'll talk about organic chemistry a bit now too, actually. So we've spoken about covalent bonding, why it happens, the structure of atoms. Yeah, that happened a while ago, didn't it? I think it's oganesosium, atom number 118. I could be wrong. I'll have a quick search just to check. My internet's taking a long time. That's not good if you're streaming. Oh, I just remembered I streamed at like 480p on my main channel. No. That's pain. I was meant to up the quality for my main channel and risk. You thought it was like meh. Yeah, no, it's oganesosium. It was a while ago. But yeah, pretty exciting. Element 118. No, it's not been discovered 119 yet, unfortunately. Alright, we'll talk about organic chemistry a bit. So we've spoken about atomic structure and covalent bonds. So now we can talk about organic chemistry a bit more. So in organic chemistry, there's 3 elements that are particularly just like everywhere, and like most stuff that's like from a human or like a plant or waste from humans or plants are going to just like consist of these 4 atoms mostly. Carbon's pretty famous, a lot of people have heard of it, and the other ones, maybe not so much. People have sort of heard about hydrogen and oxygen through water, but nitrogen doesn't get spoken about as much, sometimes in science circles. So the atomic numbers of these is carbon is a 6, it has a mass number of 12, hydrogen is atomic number 1, mass number 1, nitrogen is atomic number 7, mass number 14, and oxygen gets 8. And the atomic numbers tell you how many protons and also how many electrons, obviously when it's neutral. Never heard of nitrogen. A lot of people think that the air is oxygen, but in reality it's mostly nitrogen. I'll tell you a bit more about each of these. The key characteristic we care about, there's all sorts of characteristics of these. There's first ionization energy, second ionization energy, first electron affinity, all that good stuff. But as far as organic chemists, and therefore the people studying meth and whatnot, care about is the number of what we call valencies. So it's how many things it can bond to. And in organic chemistry, sometimes we see double bonds, but it's usually single bonds, especially when you're starting out. Yeah, but chat's getting out of hand. I don't know what to say about any of it. So yeah, these are the different valencies it can be, and you can also like stack the valencies together. So nitrogen could maybe form one double bond and a single bond. So in nitrogen gas and the atmosphere around you, what happens is one nitrogen atom which wants to make 3 valencies finds another nitrogen atom that also wants to make 3 valencies, and they come together and they form a triple bond. So you have N2 gas. There's also some oxygen and carbon dioxide there too, but it's mostly nitrogen. In terms of where these elements come from in the first place, they come from stars. So you start with protons and electrons, and you have 1 proton pairs to 1 electron to make a hydrogen atom. And then all these hydrogen atoms come together. They'll form H2 first, and then they'll come together and compress in a star, and it'll start burning and stuff, and it squashes together and it forms all the elements. You can like search about it. No, feel free to comment things. It's great to have activity, honestly. There's more that can be said about, physicists can tell you more about elements being formed, but essentially they get crushed and it keeps increasing at the atomic number, so that happens. So that's where nitrogen comes from and what it is. So there you go, now you know all about nitrogen, and biologists will go on and on about nitrogen. It's really important in like plants and stuff, for keeping them nutritionized or whatever, I don't know, ask a biologist. And it's also, it appears in meth. There is a single nitrogen atom in meth, so there you go, the more you know. Alright, I'm gonna have to finish in a bit. This has been great. Oh, there's intro to organic chemistry. That's what I was trying to think of. Alright, so we've done that. I could maybe talk about this. I really like organic chemistry, so I should probably stick on to that more. Oxidation states is pretty fun. Energetics is important, but not so fun. We'll talk about energetics a bit and what it is, rather than going into it, but very quickly. Energetics, I believe, I should probably look this up, but energetics, I believe, is just the study of energy movement. Very similar to the field of thermodynamics. I honestly can't tell the difference between energetics and thermodynamics when I looked into the research more. I feel like you have more of a chemistry education than you're letting me believe, Big, because that's a very good question. Not necessarily. 2 atoms are of the same elements if they have the same number of protons, but the other fundamental particle in atoms, not fundamental, neutrons aren't actually fundamental, but you can sort of think about them as fundamental for now. So for example, oxygen, I believe, has an isotope 1 lower than 16. So I believe, so so there's 8 protons. I'm just going to draw 4 and then put a 2 next to it because I'm lazy like that. But there's 8 protons, and I'm going to copy it and paste it because I feel like it. And in the oxygen 16 isotope, there's another how many? Another 8 neutrons. Again, we'll just put a 2. This is in oxygen 16. So we've got 4 times 2, 8 plus 4 times 2, 16. Whereas you can also get oxygen 15, where instead of 8 neutrons, you only have 7. So we'll just draw that. I'm going to draw it as 2 lots of that plus an additional one. So no, just because they're the same element doesn't make them identical, but they have the same number of valencies, so it's pretty much the same. Fun thing with isotopes is you can sometimes get heavy water. So water consists of 2 hydrogens and oxygen. So if you add an extra neutron to each of the hydrogens and you add that for every water molecule in water, you get water that's heavier. So you can get these ice cubes that sink in water because in the ice cube all the water molecules have an extra neutron, and in the liquid water there isn't, so it sinks. It's kind of cool. Called heavy water or something, or deuterium or something like that, I think. So that's pretty fun. All right. I'm glad I could answer that question. Don't know how sincere it was, or whether you just wanted to hear about isotopes. I don't know. I don't mind either way. Energetics is very similar to thermodynamics, pretty much the same thing. At AS chemistry level, you only look at pretty much just Hess's law, and Hess's law is pretty great. What it does is it tells you that the path from one reaction to another. Oh, yeah, we haven't even spoken about reactions, but they're all over the place in chemistry. It allows molecules to turn from one thing to another. So, for example, you might have hydrogen gas react with oxygen gas to form water, as an example of reaction. So we got some hydrogen, some oxygen becoming water by the atoms of the molecules rearranging themselves and whatnot. Anywho, so this is one reaction. There's all sorts of different reactions that can occur. And what Hess's law states is that if you go a different way, we call it enthalpy, but it's pretty much just energy, honestly, but just with a few extra conditions. The enthalpy change from there to there is the same as going from there to there and then from there to there, etc. So sometimes you can use this to do calculations, to calculate energy changes that you wouldn't be able to usually by stringing together other pathways. So that's all of energetics, which makes up a decent amount. It's pretty useful. It allows you to do a lot of interesting calculations. It's very analytical, makes up a lot of chemistry. Time for bed. Yay, cleared the vague. Time for bed, yeah. It's time for bed very soon. Feel free to close stream there. Thanks for joining me for that I did. Hope it was interesting and useful in any way. Crash course chemistry. Well, yeah, I'm open to feedback. I also have a Discord. If you're not already in it, you can check that out in the description. But yeah, have a great evening. Or sleep, as it seems you're going for. I'm just quickly, whether or not I get any viewers, just want to go through these. How many are there? Actually covered a lot of chemistry very quickly. Maybe not going to cover organic analysis because it's intense, and I'm not ready for it right now. I can go through the other four though, no problem. Oh, it's my alarm to say stream should end around about now. So I'm just going to go through these four and talk about them. So do that. Start petroleum, or the alkanes topic. As we spoke about before, the four main atoms and their valency numbers are carbon, which forms 4 valencies, hydrogen forms 1 valency, oxygen forming 2 valencies, nitrogen forming 3 valencies. In the petroleum topic, we just look at basically how we get alkanes, so therefore we can... Yo, thanks, Fig. Stay as long as you want to, otherwise I honestly don't mind. I'm going to put a bit less emphasis on entertainment now, because I'm pretty happy with how the first bit went, but I kind of want to just do an analytical bit on this, so I'm going to do that. So feel free to join, otherwise it's completely up to you. So petroleum sort of looks at the fundamentals of organic chemistry, being that unlike silicon that also has 4 valencies, silicon will tend to want to bond with itself in like a giant structure of silicons going like this. So all the silicon valencies are going to other silicon atoms. Carbon is weird in that it will tend to form chains like this and then have its other 2 valencies open to just all sorts. And it doesn't tend to do carbon as much. You can still get it. If carbon bonds like silicon in a giant lattice, you get diamond. It's just all carbons. Or coal sometimes as well, interesting enough. So, but diamond's like the cool one. But weirdly enough, oftentimes it will just do this. And hydrogen tends to cap off where there's just 1 valency a lot of the time. So basically what you learn about in the petroleum topic is that you can form giant chains just by stacking carbons on top of each other like this and filling out the space with hydrogen. So that's the main thing. And what they look at is, we look at this in organic analysis more, but essentially the idea is that even though we study these 4 independently, alkenes, alkanes, halogenoalkanes, and alcohols, the idea is you can switch between them quite easily using chemical reactions to swap in and out atoms. So in order to form these other 3 organic compounds, you'll tend to start with petroleum, because you can mine petroleum. Mine? Is it mine the right word? Extract. In the UK we get it from the North Sea, and it forms from old animals containing carbon and hydrogen dying, becoming fossilized, being squished by pressure and stuff. at the bottom of the seabed, and that forms fossil fuels, including crude oil, which is where we source petroleum from. Well, petroleum really is crude oil, and it contains all these alkanes. And the alkanes will be all different lengths. So this one's of length 4, but you get all sorts of different lengths. So it'll go all the way from like C1. No, C1's methane. C1's a bit different. That's natural gas. But there is some natural gas in there as well, I believe. So you've got C1, which is just a carbon with 4 hydrogens. It goes all the way up to huge numbers. We're talking like C60, I believe. And that's not like C60 like a fancy carbon ring thing, which you get. That's a different thing. There's another C60. Maybe it's C20, where it's just a bunch of carbons bonded to each other. That's 60 carbons in a row with a bunch of hydrogens around it. Another key thing we look at in this topic is the fact we can actually derive a formula for how many carbons, how many hydrogens will that result in. So the formula is where you have n carbons, you'll always have, if it's an alkane, which means it's only carbons in a single line with hydrogens either side. Actually, it can branch and it'll still be an alkane. It's basically just carbon and hydrogen only and no double bonds. Then you've got an alkane. We call that saturated when there's no double bonds. It's unsaturated where there's a double bond. That's the formula. There'll be 2 times the number of carbons plus an extra 2. So if we have 60 carbons, that means we're going to have a lot of hydrogens basically. 60 times 2, 120 plus 2, 122 hydrogens. You cover a lot in this topic actually. It seems really simple, but it's just really not. Petroleum is, even though it's a simple molecule, there's a lot to discuss here because it's your first dip into organic chemistry properly. And the other thing you look at is, of all things, pollution. Turns out this bad boy, the alkane, is great fuel, especially when there's shorter chains. It burns and gives a lot of energy. All the carbons, all the hydrogens get oxidized. Carbon oxidides into carbon dioxide or carbon monoxide if there's insufficient oxygen. And the hydrogen obviously gets oxidized to water. Well, not obviously, but that's what happens. Hydrogen reacts with oxygen to form H2O water. And it turns out because it gives off so much energy, it's a really popular fuel. But the problem is sometimes there'll be like sulfur impurities in the hydrocarbon fuel. When that burns, that forms sulfur dioxide. And also by burning these, we're producing carbon dioxide, which is obviously a greenhouse gas. That's not good in terms of climate change. So we basically look at these two things and what chemists do to mitigate that in terms of, and carbon monoxide is no good. Carbon monoxide and carbon also get released occasionally when there's insufficient oxygen, and these are really no good as well. And nitrogen monoxide as well. I don't remember where the nitrogen monoxide comes from though. The point is there's all sorts of pollutants, and we look at how we can reduce it in terms of like catalytic converters in cars to convert some of these things into less harmful things. And we also look at like flue gas desulfurization, which is handling the sulfur dioxide problem basically, because that reacts with water and oxygen in the atmosphere to form acid rain, which is bad. People don't like acid rain. It does bad things. It's bad for the ecosystem. It also like erodes away rock that easily erodes, which is no good. Okay, that's all I want to say about petroleum. That's a lot. Okay, alkenes, very similar to alkanes we just looked at, but the difference is it's unsaturated. Well, that just means it has a double bond. And when I look at halogenalkanes, I'll talk about this more, but essentially it means something can add across the double bond, we say. So there's now a slot down here, so we're going to have hydrogens up here and hydrogens down there, but there's like a gap here where 2 atoms can go in and bond to either carbon. The double bond like opens up to allow that to happen. I think that's all we cover in alkenes really. Oh, and we could look at the structure of the double bond from like an atomic orbitals perspective, and the fact that it forms like a planar bond. That's what we describe it as, but ain't got time for that. That's the alkene topic. The alcohols topic there is more to it, but I'm just going to keep it bare bones because I feel like it's going to go ham on the halogenoalkanes topic instead. There is more to it, but the essential idea is that just this classification we'll go for. I could talk about classification more. You know what I want to? I'll talk about classification a teeny bit more, but essentially if it's got this bond, this particular thing right here, we call I think it's called like a hydroxyl group, or like an alcohol group is what it can also be called. It means it's an alcohol if it's got this OH pattern type thing bonded onto a carbon like that. And then it's an alcohol. And we have, where there's just one OH, we have different types of alcohol. And it's to do with how many carbons the OH is bonded to. So here the carbon the OH is bonded to is there's only one carbon here. This carbon is bonded to. So we call that a primary alcohol. But if, for example, and we'll use skeletal. I've spoken about skeletal a bit, but not very much, but that'll be enough, hopefully. If we had this molecule, now as you can see, the carbon here, which the OH is bonded to two other carbons. That's a secondary alcohol. And then you can get a tertiary alcohol where the carbon it's bonded to is bonded with all other its free bonds to hydrogens. I went through that very quickly, so if nothing made sense there, then so be it, sorry. But that's one of the areas you look at with the alcohol topic. I mostly just wanted to introduce that that's what an alcohol is, it has the OH, and then add a bit more detail just because, you know, it's meant to be like an overview of AS chemistry, and like per usual, inorganic chemistry got so neglected, but I have no problem with that. It do be like that sometimes. Oh, and quickly while I'm here, kinetics, in case you're wondering, is I haven't got enough time to do it justice. I just won't talk about it. That's fine. Halogenoalkanes. This is the heavy hitting topic. This is where stuff gets very exciting. Oh boy. You know you like chemistry a bit too much when you get excited about the prospect of talking about halogenoalkanes. Let's first look at the general formula of a halogenoalkane. It is an alkyl group, which is this bit here, and one of the carbons of the alkyl group, well, the end carbon on the alkyl group, because it'll be like a string, a bit like a alkane, but with an extra, with one of the hydrogens missing. It will bond where the hydrogen's missing to X, where X is a halogen. We need to talk about the halogen. For that, we need the periodic table. Oh, you know the chemistry is getting advanced when you actually need a periodic table. And by the way, although I've like not used it much, oh, I lost my viewer. That's fine. Yo, he's back. Hello. I'm not going to complain. Pun intended. Thank you very much. Yo, Big, by the way, you that new user who joined my Discord? Yeah, adios. Fair enough. I'm surprised you stayed so long. I appreciate it. Yeah, I really do. Have a good one. But I'm just going to finish off halogenoalkanes and I'm going to call it a day as well. Alright. Oh, we're still here for a few seconds. I was just going to ask if you were the same. If you leave, that's fine. I was going to ask if you're the same user that was on the Discord. I don't know if I get a response, that's fine. So anywho, the halogens are these ones here in group. And what's written as group 17 here. One left from the final group on the right, and the groups are the columns. So it contains fluorine, chlorine, bromine, iodine, astatine, and tennessium. But tennessium and astatine are so scarce that essentially it's just 4: fluorine, chlorine, bromine, iodine. But then of those, we sort of ignore fluorine a lot of the time because it doesn't follow the trends that the other ones do in terms of its reaction. Because when a fluorine bonds on, it can't come off because of the reactivity, because of the bond strength, sorry, between the fluorine and the carbon. So it only works for bromine, chlorine, iodine. I was going to talk about mechanisms a bit. I'll talk about it ever so slightly. We won't talk about free radical substitution, unfortunately, but that is a thing we do. But in addition to free radical substitution, the other three mechanisms we mostly look at in AS chemistry. Wait, no, I was meant to keep it shorter to keep it be watchable for non-live viewers on my main channel, because longer videos are no good, really, for the style of video I make. Oh well. So there's nucleophilic substitution, elimination, and electrophilic addition. I wonder how much of those I can go into. Nucleophilic substitution is not too bad. Essentially just, we use an R to describe an alkyl. I haven't got time to go into what's going on fully here. But essentially, nucleophilic substitution, you get a nucleophile. There's some different nucleophiles. You have CN minus, which is called a nitrile, which is a nucleophile that can do this. There's OH, which we've sort of seen before, so I'm going to use that as my example, I think. We also have, what other nucleophiles are there? Oh, there's ammonia, NH3. So if we use, you can put any X halogen here, which is either bromine, iodine, or chlorine. We'll use bromine as an example here. Essentially what will happen is I'm just going to use this as part of this reaction because I can. It's called a reaction mechanism. Essentially this can come... Oh, please tell me it's double arrows. I'm pretty certain it's double arrows, so it should be alright. Essentially go like this. The arrows don't show movement, they show movement of electrons. So the electrons are there are going to that. And that's going to there. So this thing could be moving here, but the electrons could be going that way, in which case the arrow could be going the other way. In this case it's not, but just worth being aware the arrows aren't movement, it's electrons, how they move. This will result in the bromine being displaced, but the OH attaching and forming. This will now form an alcohol. I'm going to draw out the bond actually. So that's through nucleophilic substitution. There's a bit more to it in terms of what chemicals you use to make it happen and stuff, but that's the main thing. This is sort of an overview of like a lot of AS chemistry. Well, not a lot. I don't know how much AS chemistry I've done. Quite a bit considering everything. All right, how long am I going to look at the other two? Not long really because I'm tired, but a bit. We'll look at electrophilic addition first. So this allows us, as you've probably seen, halogenoalkane, by the way, is just anything of this form. So it's just an alkane, but then one hydrogen is replaced with a halogen. So this allows halogenoalkane to be converted to alcohol. It's one of the conversions you can do with it. Electrophilic addition lets you convert from an alkene to either an alkane or a halogenoalkane. And then elimination allows a reverse, so you can turn, no it doesn't, it just allows you to turn halogenoalkanes back into alkenes. So that's what these different things are. That's very quick, so don't worry if you didn't get that. The point is you can convert between different molecules using these mechanisms, and you can set the mechanisms by taking some chemicals, dumping them in a container or whatever, and this mechanism that we're drawing out sort of occurs, and you get the conversion occurring. Okay, we're going to start with electrophilic addition because it's a bit easier. We've spoken about the R's very briefly, but if the R doesn't mean anything to you, it doesn't matter really here. This is a double bond. And the R prime is the same as an R, it's just we're saying it's a different R to this R, so that's why it's R prime. But if you wrote two R's, it really wouldn't matter. It's more the idea of the fact there's more stuff on this side of the compound and more stuff on this side of the compound. So if we, let's use an example because it'd be easier. We haven't spoke about bond polarity, but I'm going to talk about ever so slightly now. I mentioned earlier how a covalent bond for every, so for example, single bond 2 electrons, double bond 4 electrons, triple bond 6 electrons, etc. So here it's a single bond, so there's 2 electrons, but they don't sit directly in the middle of the hydrogen and the bromine. Depending on what we call the electronegativities of those two atoms, it will get pulled slightly more this way or slightly more this way. So bromine's a lot more electronegative. It's like, what's the electronegativity of bromine? Oh, it's not too high. It's I could be wrong, but I believe it's 3.0 on what's called the Pauling scale. Hydrogen's only 2.1, so the bromine will take more of the electrons and it'll become slightly negative, which we notate like that, partial negative. So this is partial positive, electrons are negative, so therefore the electrons in the bond here are going to tend to move onto the slightly positive hydrogen. And then as that happens, the electrons here move onto the bromine. I'm not going to draw the whole mechanism, there's a few different steps. But essentially, with this being the starting point of the mechanism, you can essentially force the hydrogen bromine onto the molecule. And that's what electrophilic addition is, I was sort of talking about earlier. So that's why we call it unsaturated when you have a double bond, because the electrophilic addition can happen, and you'll fill it out with the atoms. Alright, nearly done. Being a 6 stream, how have I got 2 viewers now? I'm not going to complain. Hey viewers, how are you? Anyone in chat? If not, that's fine. I was just closing the stream and things got less entertaining when people came back. Maybe it was better than I thought. I'm not going to complain. Or people only just saw the message in my Discord. Oh, I scared one viewer off, that's fine. I was so surprised. I wanted to just react on the fact I got 2 viewers all of a sudden. I don't even care if that made the stream less good, so they left. Oh, that's jokes. Alright, final thing, elimination, and then I can sleep. So elimination occurs when you have a halogenoalkane. There are some more conditions, but we won't go into that. We're assuming all things that need to be assumed. If it's all set up such that it can happen, I won't go into why that happened. But if it's going to happen, this is how it's going to happen. Alright, we're going to go into the mechanism of that. It's a one-stage mechanism, which is fantastic because I don't want to write out more than one stage. And she saw me going with the electrophilic addition. Oh wait, there's more stages. I'm not doing those stages. So the setup will be that it will have the R prime like this, and you'll have some hydrogens up here. And the bond can rotate and stuff, and you can draw it differently. So if the bromine's not quite on top, sometimes you can redraw it such the bromine's down here. You don't have to put the bromine on the bottom for doing the mechanism. I just find it's easier to. For me, it was just easier to configure it like this. I don't know why. So you get your OH, you can draw it either way around. Like I was saying, the atoms, the molecules can rotate and stuff. So it's the same thing. So an OH still, we've just drawn it with the hydrogen there because we need the oxygen on this side here. So the electrons on the oxygen will move to this hydrogen, and then you'll get like a wonderful cascading type mechanism. I hope all these mechanisms are right. If they're not, then I'm going to cry, but we should be good. I mean, with the electrophilic addition, I wrote so little of the mechanism, it's hard to be wrong when you write that little of it, but it should be fine. Watch me just do this whole stream on mute. No, we didn't do that. And this will result. Maybe you can see what it results in. I would ask my one viewer in chat if they could guess, but I don't know. I'm gonna wait and see if they can type in chat and if they can guess what forms. Probably not, considering just how quick this crash course type thing was. I can't speak. I'm gonna assume that I'm not gonna. It's an alkene. I think I might have said this earlier, but it's pretty cool. So the electrons here move on to here to allow the double bond to form there. And yeah, what's left over is the HO bonds with the H to form H2O. That's pretty sick. So yeah, your H2O, and the bromine comes off, and it has a charge. I'm not going to talk about why it has a charge. You might be able to see why, but it does. And the key thing of reactions is the overall charge here will be the overall charge here. So we've got a 1- charge here. We've also got 1- charge here. So that's quick detail no one cared about, just because why not? And we covered everything. That's the halogenoalkanes topic. You sort of look at what halogenoalkane is and sort of the fact that it's quite useful in conversions. We skip through radical substitution, like I said, but that's another one that you look at. So that was pretty crazy little crash course chemistry thing. I hope you enjoyed. In terms of, I made this mostly because I was like, wait, the unis I applied to and they got on my YouTube channel, wait, hold on a second, there's no chemistry videos. So that was like the main thing, to be like, there's at least one chemistry video, there's 2 chemistry videos on my other channel called Computer Scientist, which are now being featured on my main one. And that's all really. Pretty wild video, hopefully it was okay. Seemed pretty alright. I got quite a bit of viewership, some of it. I hope you guys have a great week. I really need to sleep now. Have a good one, bye.